Okay, this is going to be your lecture video for Chapter 4, the very beginning of Chapter 4, 4.1 to 4.3, where we're going to talk a little bit about solutions. Now, solutions are a type of like mixture, basically. And what's happening is we're basically mixing two materials together into a homogeneous mixture. Right. Now, a solution specifically, there's some terms that come along with it. One is that the majority component of a solution is called the solvent, and then the minority is called the solute. And so sometimes we do this based on mass, sometimes it can be on volume, but really whatever you have the most of is going to be your solvent, and then whatever is less than that is going to be the solute. So you can only ever have one solvent, but you can have many solutes, depending, right? So solutions, they form in part because of the intermolecular forces. And so what's going on is that those materials, instead of those solute particles being more attracted to each other, they actually will start to interact with the solvent particles to mix themselves up. And so they're more attracted to the solvent particles than to themselves based on how many solvent particles they can interact with and things like that. And so that's how our solutions can form. Now, solutions, we generally think of it as being a solid inside of a liquid, but in reality, it can be a lot of different kinds. It can be gases and gases, gases and liquids, liquids and liquids, solids and liquids, solids and solids, and any type of combination between there. So we're not limited to our solutions only being when something like sugar is dissolved in water. It's not only tied to that. You can have solutions in a variety of different types. One type of solid and solid one is called alloys. And so that's when you might mix something like copper and zinc together to form brass. But even air can be considered a solution, is just all gaseous phase, gases and gases. So you can have all of these different phases together. The important part is just that you have a homogeneous mixture at the end. So we have to be able to mix it well enough that they are homogeneous. Now, inside of our solutions, they can be further split into two categories. One is called an electrolyte, and then from there, there's a smaller subset called acids and bases. So electrolytes, it's a medical term, but it's also a chemical term. And what electrolytes mean is that that solution can conduct electricity. It has the ions needed inside, so it can conduct electricity, whereas a non-electrolyte doesn't conduct electricity. Now, inside of that, acids and bases are a smaller subset of that. They are a subset of our electrolytes. So all acids and bases can conduct electricity, but they form a very specific set instead. So this is a common list of electrolytes on the left, non-electrolytes on the right. And I want you to take a moment, pause, and think, can you come up with an idea about what's the difference between one of them over the other? What do all of our electrolytes have in common that maybe our non-electrolytes don't have in common? Can you classify those compounds differently? And so, going off of that idea, maybe we just need to elaborate a little bit more about what electrolytes talk about, how they work, and maybe that might clarify things for us. So electrolytes, they're mobile charged particles in that solution that carry those electrons back and forth, which allows our electricity to flow. So if you imagine this light, in order for us to flow electricity, we have to carry that electron from one side to the other in order to complete that circuit. Now it does that because it has ions inside. So they carry the currents in the electrolyte solution, and it's because they have these ions. So when we look at this list, we want to think about, well, our electrolytes, they all form these ions. And the reason why is they're all either acids or they're ionic compounds. And that's because when an ionic compound dissolves, it does something called dissociating. Instead of staying together as a molecule, it instead splits up into the ions. So we get NaCl splitting up into Na plus and Cl minus. So we get our ions that form, our positive ions and our negative ions. On the other side, our non-electrolytes, they stay as molecules, so they don't dissociate when they dissolve. So something like ethanol, when ethanol gets into water, the ethanol molecules stay together as a team, but those teams of ethanol molecules will separate, right? So those molecules separate from each other, but they stay all together as one unit. And so that's the difference between using the term dissolving and disassociating, right? All materials can dissolve. Only ionic compounds can dissociate because they are turning into their ions. So dissociating means that you're forming ions. So our electrolytes, they all dissolve in water and they dissociate into ions. Non-electrolytes dissolve in water without producing ions and will not conduct electricity. This is why when you exercise a lot, they tell you to rehydrate with electrolytes. It's because when you exercise a lot, you can sweat out the salts inside of your body, and those salts actually are really important because a lot of chemistry in your body relies on those different salts. Sometimes it's for carrying electrical signal between your cells. So like your nerve cells, you rely on electrical impulses to work. But also some of them are just involved in your everyday processes. And so they want to replenish those electrolytes that you might have lost through sweat. And so that's why they encourage you to drink electrolytes. But some of those can be replaced as something as just eating some salty food, drinking some water. So it just all depends on what electrolytes you're looking at replacing. So which of these do you expect to be electrolytes and which ones do you expect to be non-electrolytes? So take a moment, pause, figure that out. Now, the top one is definitely an electrolyte. We have aluminum and we have it with a polyatomic ion. So that is definitely an ionic compound. We have a metal and we have a polyatomic ion. The second one, B, that's all just nonmetals. We have no metal in there. That's called methanol. So that is going to be a non-electrolyte. And then the last one, KBr, that is going to be an electrolyte because that is an ionic compound. So when they're asking you if something's electrolytes or non-electrolytes, really they're asking you, is it something that's going to form ions? So be thinking ionic compounds, polyatomics, things like that. Now, inside of that category of electrolytes, we actually have two classifications in there as well. And so we can talk about the strength of that electrolyte. So we might say that's a strong electrolyte or that's a weak electrolyte. And so a strong electrolyte, what that means is it basically completely dissociates in water. So almost 100% of it will be in ion form. So that means something like NaCl is what we consider a strong electrolyte. When we put it inside water, all of it goes into Na plus and Cl minus. Now this is different than something that is a weak electrolyte. So a weak electrolyte only partially dissociates. And so a really common one is HF, hydrofluoric acid. Hydrofluoric acid, some of it will turn into H plus, some of it will turn into F minus, but there's still a noticeable amount that stays together as HF. So it still dissolves, that molecule is still getting mixed with our solvent, but some of it stays together as HF. And so that's a difference there that we want to make sure that we pay attention to. So if you have a strong electrolyte, it means you can safely assume everything's turning into ions. So you have none of that NaCl left. You can't find it anywhere. If you don't, if you have a weak electrolyte, it means that yes, you do have some of the ions present, but you also have that HF present. So remember, weak electrolytes contain both the original compound, but they also contain the ions. So we should be able to classify this as either being a strong electrolyte, a weak electrolyte, or a non-electrolyte. So Na plus is a strong electrolyte. We don't see any of those Na plus or Na fluorine, so sodium fluoride, stuck together. HF is a weak electrolyte because we see some ions, but we also see some that stuck together. And then F2 is considered non-electrolyte because none of them have turned into ions. And so that's what you're looking for in a diagram like this. A strong electrolyte won't have any of it stuck together. A weak electrolyte will have some ions and some stuck together present, and then a non-electrolyte will have none of them separated as ions. Now, when table salt is mixed with water, it seems to disappear or become a liquid. That mixture is homogeneous, right? So we see it all mix in there and dissolve. And so that's what an example of our solution is. And so in this case, the water is going to be our solvent because we have the largest component of it. The salt, the table salt, is going to be our solute. Now, pure substances can't be a solution. What that means is if it's just a substance by itself, it has a constant composition, and so it's not going to be considered a solution. This only works if you have a mixture, so there always has to be two materials present. So in order to do that, we have to be able to describe both parts of those pure substances inside that solution so we can accurately paint that picture. So there's a couple ways that we talk about solutions. We might talk about it qualitatively, where we might just give an idea if we have a lot or a little, or we might come up with a quantitative measure where we actually give a value to it. So an example of solution concentration is something like a dilute solution versus a concentrated solution. So a dilute solution just has a small amount of the solute compared to the solvent. So we have less of it in there. And so this is something like if you water down your orange juice, you're diluting it because you are taking that orange juice, all the sugars in it, the flavors of it, and you're adding in more water, which is the solvent in that case, and we're making it so it's not as often, not as frequent, so its concentration is going down. Concentrated solutions have a large amount of it. Right? And so generally concentrated and dilute, we use that when we're comparing it against one another. Right? There's not values that go with concentrated versus dilute, but we're comparing them one thing to another. So you might have two solutions. One is going to be the concentrated compared to the other one, which can be the dilute. And so we're generally doing that in comparison to each other. It just gives you a rough estimate. A better way is generally to use something that might express the value, the amount of the solute in there. And so one of those concentration terms, the first one we're going to introduce, is called molarity. Now molarity, it stands with a big M, which is why when you've been writing your units, we try not to use that big M for things like moles, right? We use MOL for moles because that big M stands for molarity. And molarity is comparing our amount of our solute, which is that top part, and the volume of our solution down at the bottom. So remember that the solution, this is your solute and your solvent, whereas the top is only the solute. So this molarity is giving us the moles of something versus a volume. So it's a concentration because it's the amount of material over some amount of space. So when we're looking at this, would be how we can prepare something that has 1 molarity of NaCl in a 1 liter solution. We weigh out the 1 mole of the NaCl. We then add in that solvent, which is our water, until it starts to dissolve. Once we get it all dissolved, then we fill the whole thing to 1 liter, giving us that value. So if we looked at that, we would have 1 mole of NaCl. We'd have 1 liter of solution. And when we divide that, that's going to give us our 1 molarity. Now, if we know that 1 mole to be 1.00 moles, and we know this volume to be 1.00 liters, then we can get a molarity of 1.00 molarity. So we can use this molarity in our calculations when we talk about solutions. And so we can use this either to convert things from our volume into moles or from our moles into our volume, depending on which way we use it. So it's just another conversion factor for us. Now, when we start to make stock solutions, so that means we have one solution, we're converting it to another, we start to see equations that look like this. M1V1 equals M2V2. And this is a fine equation when we're talking about dilutions. Right? It helps us say that, well, if we start with one solution, it has a molarity of 1. So let's say that it's got a molarity of 4.00 moles of 1 liter of solution. And we want to figure out what volume of it we need. So that's the volume of solution 1 in order to make a second solution that is less than that in its concentration. So let's say 1.5 moles of 1 liter at a volume of 202.5 liters. Now, what that does is it sets one side equal to the other. And so we get something like 4 moles over 1 liter is equal to 3.75 moles. So when we divide this by our moles per liter, we can get the volume as being 0.9375 liters or 0.938 liters. And we can find the volume that we needed to transfer that. Similar to what they're doing here. They try and figure out how much you need from one to the other. My issue that I have with this equation is that I don't think that it's necessary. I don't think that you have to memorize this equation in order to make that work. Instead, think about what you're actually doing and then use that as your connecting piece. If we have one solution here and we're making a second solution over here, what we're transferring in there, the moles of that solute is going to be equal from what we transferred from solution 1 to what's inside solution 2. So if this is our solution 2, this is our solution 1, all of that solute that's there is going to be equal to each other. So instead of thinking M1V1 equals M2V2, look at what moles are actually equal to each other, because we can always figure out how to get back to moles. So I just want to point that out there, because sometimes when we start to rely on this, we run into problems because we start to do this anytime we talk about one solution and another solution. And it doesn't work like that if those moles aren't equal to each other. So if we do a titration that uses a different chemistry that's not one-to-one, then this will all fall apart. So you just want to be aware of that. So let's try this. What is the molarity of an aqueous solution containing 22.5 grams of sucrose, which has this chemical formula, in 35.5 milliliters of solution? So we have to find the molar mass of C12H22O11. Then we also have to find how many moles that's going to be. So let's find our molar mass first. We have that as 222.17878 grams per mole. We know we have 22.5 grams of it. So if I divide it by its molar mass, that gives me its moles. Should have 3 sig figs there. We have our milliliters, 35.5 milliliters. Now I don't want it in milliliters, I want it in liters, so I need to multiply that by 1 liter is 1,000 milliliters. And then if I want molarity, then I just take my moles, 0.101 moles, divided by my liters. And we get our value 2.85. Let me just double check this because our value isn't lining up. Ah, that's what the issue was. This shouldn't be 220. This should be 342.29648. Had the wrong molar mass there. It changes everything. Always a good idea. Double check your math. And so instead of 0.101 grams, I really have 0.065. And then when I divide that by my volume, we get 1.85. And so we're looking for the answer C. All right. There we go. So we can use this for all of our solution stoichiometry, and we're going to start to see this a lot as we go through our next couple of steps, right? And so you want to get more and more familiar to this. This is now a new addition that you can add to your stoichiometry diagram. So in the same way that before you had moles and you used to only be able to get there from a mass, now we can add in this pathway down here as well. We can also get there from a volume of a solution if we use our molarity. All right. Now, the next step of solutions is we need to talk about a couple of different types of reactions. So one of them is called a neutralization reaction. So neutralization happens when we have an acid and we have a base, and they're going to neutralize each other to form water. And so the idea behind it is that an acid produces this H plus inside of water, and a base generally produces a hydroxide. And so when they come together, we're going to see water that gets created as a product. Now, as we move forward further in this class, we will get more specific about our acids and our base chemistry. But for now, what you want to look for is you want to look for an acid, and then we're going to look for something that contains a hydroxide on the other side, and then we'll follow this pathway up here. And so this is the basic idea between it, is that we have an acid and a base, and then we're going to make some water afterwards, and then we make what we call as a salt. So the salt is left over. So the reason why we're talking about this early now is because we're going to be interested in this for our lab this week, and it's called a titration. So a titration is where you use a substance inside of a solution that we know its concentration. We're going to react it with another substance inside of a solution where we don't know its concentration. So we're going to react them together until we find the end point where we know that the reaction has gone all the way to completion and not anymore. This can also be called the equivalence point. The equivalence point is where we have the same amount of our titrant, which is equal to the same amount of the analyte. What that means is your titrant is the one that we know. Whatever's in our solution, that's our unknown. And so we're trying to find their amounts. Right? So we're using this unknown, we're using this known solution, and we're trying to record equally or very closely the amount of volume we put in there because we know its concentration. Once we get its volume, we can turn that into moles, which is the amount of material, and then we can figure out how many moles it had to react with on the other side. So the unknown is normally, so in our case, we're going to have a known amount of our acid, we're going to have an unknown amount of our base, and that's what we're going to be looking at trying to do. Now, in acids and base titrations, we are generally looking for something that is going to let us know when they have finally neutralized, when they've come to a transition point. And so that's called an indicator. So in the same thing, how I was adding in indicators to our last experiment, where we were trying to identify acids and bases based on the color of that solution, we're going to see a similar pathway. And so we're going to add an indicator to our titration in order to be able to tell when that happens. And so when the indicator changes its color, then we know whether we've met that endpoint or that equivalence point. So if we do this correctly, our endpoint should equal our equivalence point, because our equivalence point is what we're looking for. That's when those values are known or unknown have the same amount of material. The endpoint is simply where you stop. It is generally done by our indicator. So in this example, they're using our base up on top, our acid down at the bottom. We're adding in that solution, and our indicator is going to turn pink when it finally hits that end point. So it's clear, clear, and then all of a sudden it's pink. This is the same titration as what we're going to do in lab. And so from here, we're using this indicator of phenolphthalein. And so you can see it starts off clear, and then after one drop, sometimes even half a drop, it's going to turn pink. And so then we can use that information to tell us how much of our unknown solution there was. So let's say that we know the concentration of our HCl. We are trying to figure out what volume we're going to need to transfer if we have a concentration of our calcium hydroxide and 100 milliliters of it. So we want to write out our reaction first. So our HCl and our calcium hydroxide is going to go into, and that's an acid and a base. So we should make our salt and we should make our water. So this is just a funny way to write in our H2O, because it's trying to show you the H plus, which is coming from the acid, and then the OH minus, which is coming in from your base. So you can also have that just as H2O, either one. We got to go ahead and balance that, make sure that we have that balance. And so what we're looking for is we're looking for what volume of that HCl we need. We know its concentration. We know the volume of our calcium hydroxide, and we know its concentration here. So we can try to use this M1V1 equals M2V2. We would have our 0.5 moles of our X, 3.0 moles of our 100, and we would find out that we would need 600 milliliters. Now, the problem that we run into with this one is that the HCl, if we're looking for the moles, it's really our molarity times our liters. Our moles of it is 0.3. And our calcium hydroxide, the moles of it is also 0.3. So this is what we get if we use our M1V1 equals M2V2, because we said that their moles should be equal to each other. But when we go back and we look at our reaction isn't a one-to-one. It doesn't just take one HCl to neutralize that one calcium hydroxide. It takes two of those HCls in order to neutralize that hydroxide. And that's because that calcium hydroxide produces two hydroxide ions for every one calcium hydroxide. So if we only put in 0.3 moles of each, we're not going to have enough in order to neutralize that reaction, because we have 0.6 moles of that one. So what we need to do is we need to go back and we need to add in more. So this one up here, instead of treating it like it's only 3 molarity, we really treat it like it's 6. In that we're going to scale it based on the fact that it makes twice as many hydroxides as it dissolves. And then we can update that and we get the correct volume that we're going to need. So instead, what I would do is I would take my calcium hydroxide, and so we know its molarity. So we know that it's 3.0 molarity. We know that its volume is going to be our 100 mils. And so I'm going to take my solution, I'm going to take it and turn it into moles of calcium hydroxide. Then I'm going to change that into moles of my hydroxide. And then I'm going to change that into moles of my H plus to turn that into moles of my HCl. So my moles of my calcium hydroxide is 3.0 moles per liter, 0.100 liters. That's me just taking this milliliters, turning it into liters. Then from there, let me go ahead and clean this up a little bit, make this easier to follow. I know that 1 mole of CaOH2 makes 2 moles of hydroxide. Right? We have a ratio there. I know that 1 mole of hydroxide makes 1 mole, or needs 1 mole of H plus, and that's from our H plus OH minus going to water. And we know 1 mole of H plus comes from 1 mole of HCl. And so now I can change all of that to get my moles of my HCl. And then if I want to, I can actually sneak it in at the end. If I want to get this to a volume of HCl, well, we know that concentration, we know 0.5 moles of HCl is 1 liter of solution. And so now we can do that whole chain. We can solve that problem. And so that's why I don't necessarily use this M1V1 equals M2V2. I feel like it's just another equation that I have to memorize. And so I just go ahead and go right to my moles. Right? So it depends on what you feel most comfortable with. Now, to start working with these problems, some of those titrations are going to be pretty straightforward where we have a lot of that chemistry provided, but other ones, we have to be able to figure out what that chemistry is. And so we have to look at that dissociation and that ionization of things, right? So dissociation, that is the process where when the ionic compound dissolves, it forms the ions. Now, we want to make sure that we understand what ions are being formed. And so we should be able to look at any ionic compound and figure out, well, if it was to dissociate, what ions is it going to produce? Strong acids, they do the same thing inside of water. They're going to ionize as well. They form our H pluses, and then we have the other anion that forms with it. And so we are going to start practicing some of those. And so this brings up this idea about solubility, because not all ionic compounds dissolve in water. Some of them will stay together. And so the difference in those terms, one is called soluble if it dissolves in the water, and the other one's called insoluble if it doesn't. So if we add something like silver chloride to water, it just sits at the bottom, it settles there. In the same way that you might have a glass of water and there might be stuff that stays inside at the bottom, whereas other compounds might dissolve, things like sugar and salt, they dissolve quite readily inside the water. And so it depends on them. So we have these different parts. Now, if we mix in a solid, we want to know whether it's going to dissolve and turn into ions or whether it's going to stay down at the bottom as a solid together. And so there's one way to do it, which is just, go out, try it, see what it's called. This is called the empirical method, right? And so that's one solution. It's not, in some ways, it's the most reliable because you're going to find out for sure whether that thing dissolves or not. In other ways, it takes a lot of work. You have to then try every single one in order to do it. Instead, we're going to introduce what we call is the solubility table or products, right? Sorry, not solubility products. These are the solubility rules. Now, they're in your book, but I've also gone ahead and written them here. Now, our solubility rules, all of the ones that aren't in red, these ones here are on your equation sheet, so I will provide them for you. And the reason why is that these have these different caveats to them, right? So it's like an ionic compound that has an acetate ion. They're all soluble except if it's with the silver, right? So they have all these exceptions, and I don't think that it's worth it to make you memorize all the ones with exceptions. However, we also have these other three which don't have any exceptions to them. So these ones in red, we need to memorize. So you want to write those down because you need to know these three rules, but all the other ones you have on your periodic table that you guys can refer back to. And it's because these three are always soluble. So there's no exceptions to remember for that. So it doesn't matter what you have partnered with sodium. It could be a chlorine, it could be an iodine, it could even be carbons. If you have sodium, it's going to dissolve. Right. Now, this table gets a little bit complicated. It depends on a lot of different things. The temperature can impact your solubility. The concentration, so how much of it you put in there, will impact it, because even things like salt, NaCl, at some point it will stop dissolving inside of water. It just takes a real large amount of it. But this is just general rules, right? When you move into Chem 121, then we'll get more specific about trying to determine the exact amounts that dissolve into them. But this is our general rule that we're going to follow, right? So this is to help us out with that. And the reason why is because when things don't dissolve, they create what we call as a precipitation reaction. So a precipitation reaction is when a solid forms when we mix those two solutions. And so the reaction that's going on, the ionic compounds that have been dissociated, they form a new ionic compound that's insoluble. And that insoluble product is called the precipitate. You've seen this inside of our observing chemical reactions for the household chemicals. Those white solids that we were forming in there, those were precipitation reactions. And so this one here is a video. And so in this one, we're taking lead 2 nitrate and potassium iodine. And when we mix them together, they're forming a new compound, lead 2 iodide, which is this yellow solid down here at the bottom. It also makes this second compound that is soluble, this potassium nitrate. And so that's what's going on there. So using our solubility rules, we're going to be able to predict whether we have a chemical reaction or not, whether we form this precipitate down here or if we don't have anything that forms. So precipitation reaction doesn't always occur, but it can. And so what we need to look at is we have to look at our products. So in order to do this, we have to predict the products that are going to be formed. So the first part is determine your ions. Once you have your ions, then you can figure out what possible products you can make. So we do an exchange on them. And then once you have all of the products that you can make, you can look at the solubility of each product in that water. If none of them precipitate, then you write no reaction. If something does precipitate, then you can write that as the product. So this is an example. So in this one, we're looking at that same chemistry we did before, so Ki, and we're adding to it lead nitrate. So we split those into our compounds. So we have K plus, I minus, K2 plus, NO3 minus. And so then we're looking for the combination of what we can make from them. So our new combination is going to be our cations with our anions, because we can't put I and NO3 together, because if they're both negative, then there's no attraction between them. In the same way that we can't get potassium with our lead, because there's no attraction because they're both positives. So our new products is going to be KNO3 and PBI. So if we jump to our solubility rule, we're looking at Ki, we're looking at PbNO3. Now when we look at this, we have our lead 2 nitrate there. Well, it's got nitrate in there, so it's soluble. So that's not going to turn into a solid. That's going to be aqueous. And we have Ki there. That's going to be soluble as well. And now when I wrote this down, I realized I wrote down the reactants. So let's go back. Let's look at our products that we formed. So we are making PbI2 and KNO3. So now for our products, when we look at this, our K and our potassium and nitrate, both of those mean that it's soluble. There are rules. Our lead iodine, we can start at the top and start looking down. And so we get to this one here, and it says that all ionic compounds containing chlorine, bromine, and iodine are soluble except for, and then it goes through and lists them, and we have PbI2 there. So that means that PbI2 is not a soluble substance, so it's going to be a solid. And so then we can have that for our product. And so that's how we can figure out whether it's a solid or not. So these are two that you can practice. You can go ahead and predict them. So go ahead and break them into the ions first, and then look at what they would form from there. Try to figure that part out. So we have our ions that form, we break that down, and then we can check for our solubilities, whether or not it's going to be solid or liquid. I realize that this is a little bit stuck there. That's better, right? And so you can go through and you can try that one out. Now, to write these equations can be a little bit tricky, and so there's several different ones that we have to do for it. There's different types of reactions. So we can have what we call as a molecular equation, and that's what we've seen so far, where we leave everything together. But sometimes that doesn't give us a good picture about what's going on. And so in solutions, because things dissociate, then we really want to think about them as being independent particles kind of floating around out there, because inside that solution, this K plus and this hydroxide are free to do different things. They're not tied together anymore. And so that next step is called a complete ionic equation. So for a complete ionic equation, we basically are taking all of these different compounds, and we're going to disassociate them as much as we can. So if it's something that is ionic and dissolved, then we're going to show them all apart into ions. If it's something that's not disassociated, so like this solid here, that's not dissolved, then we can leave that together. So the rules for your ionic equations is anything that's drawn as an aqueous one, go ahead and separate them into your ions. Anything that's insoluble or weak or a non-electrolyte, then we can leave them as their molecule form. Right? So solids, liquids, and gases don't dissolve, so we leave them in the molecules. And that's why MgOH gets to stay as it is. So a complete ionic gets its name because we're going to make everything into ions as completely as possible. So breaking them all down. So this is an example of a complete ionic equation again. Right? We have our lead nitrate split up here. We have our K and our Cl split up here as well. And then we have our new products. These two are split up because they're soluble. And we have our PbCl2 there. Now, on top of this, there's a third type of ionic, or third type of equation that we can write, and it's called a net ionic. And so what we're looking for is what we call a spectator ion. It means that these are ions that are there in the beginning of a reaction and still there at the end. And so they're just watching that reaction take place. And because they're just watching, then we're going to go ahead and start to remove them in order to kind of simplify the picture of what's going on. Now, there are times where it's important to include them because they are in that solution. They can change chemistry going on into the future, but sometimes we just need a simpler picture of what's going on, and we don't need all of the other clutter. And so a spectator ion is going to be something like K plus because we have the exact same amount and the same ion on the other side. Something like NO3 minus is also the same. But our lead 2 plus is not a spectator because it doesn't show up as its ion on the other side. It's changed now. So even if it was lead 2 plus on one side and lead plus on the other, those would not be spectators of each other. Spectators have to be the exact same from one side to the other. We should also have the same ratio of them from one side to the other. So up here is an example of a complete ionic. I've gone ahead and I've removed my spectators from it. And so this is an example of a net ionic equation. And so we should be able to write all four of those different types of equations, our molecular ones, our complete ionics, and our net ionics. Now, the steps for doing that is start off by writing your equation first and then balance it. Because once you balance it to begin with, all of your complete ionics and your net ionics will also be balanced as long as you're finding the right ions from there. And then our last question for that is, what are the spectator ions? So the reaction we're looking for, it's sulfuric acid and potassium hydroxide, and it's doing something called a neutralization. So remember, the neutralization means that we're going to make water and we're going to make a salt on the other side. So a salt is just another word for an ionic compound. They get their name because a lot of them taste salty because salt is an ionic compound as well. So looking at this, we have our H2SO4, which is also a ferric acid. We have potassium hydroxide. Both of those are aqueous. We're then moving that into potassium sulfate and our water. Water is a liquid, right? Not soluble. From there, we balance it. So we need 2 of those potassium hydroxides in order to make that work, but we also make 2 waters on the other side. Then we can break it down into our complete ionic. And so this is our products over here. They've just been shifted in because they didn't all fit there. And so you can see I've broken apart my acid, I've broken apart my base, I've broken apart my salt because it's soluble, but we leave this one together because it's a liquid, it's not dissolved in there. And so my net ionic looks like this, and your book likes to actually simplify it and write it like this. And so either one is fine. So remember, for your homework, if you're struggling with it, simplify your reactions. That's how your book prefers it. All right? And so then we have a couple more examples of that. So you can keep working your way through. Writing net ionic and net ionic equations, they just take a lot of practice. So I would really strongly encourage you to do that. It'll also let you help practice finding out what products you can make, what are your different ions inside, right? So for these, I've given you them. So you can practice that. Same with this bottom one. But from there, we've also, I'm also going to link a worksheet inside this lecture. And that worksheet, let me pull it up here, is going to allow you to get some more practice with your net ionic and complete ionic equations. But the difference is I'm only going to give you the reaction part. And so you're going to need to translate that into your equation and then from there into your products. So let's take a look at this first one. Now, when I'm looking at this, I know that this is going to be my first equation, sodium chloride and lead 2 nitrate. So I need to translate that. So sodium chloride is NaCl. Right, sodium and chlorine, 1:1, because that's the ratio that I need. And then I have my lead 2 nitrate, so that's Pb. It has a 2+ charge, so I need 2 nitrates to it. I can check my solubility rules to find out if they're soluble or not. So this is aqueous, this is aqueous. And so now I need to figure out what products I can form for it. And so this is our molecular equation that we're writing there. And so what I like to do is I make these boxes. And so I can split up my 2 compounds. I don't have to worry about this box because that's pluses and pluses, and this box that's pluses and minuses. So I can make my compound between lead 2 and my chlorine, PbCl2, and my sodium and my nitrate. So we have our 2 possible compounds, PbCl2, NaNO3. And then I can check my solubility table. So I know NaNO3 is soluble. And when I look at my lead chloride looks like it is going to be soluble, but it depends on my concentration and temperature. So in this case, I'm going to go ahead and leave it as a solid. So this becomes my net ionic. I need to balance it out. Oh, sorry, not my net ionic, my molecular equation. I need to balance it out there. I can then take it into my complete ionic. So that means that I need to separate them. So I should get 2 Na plus aqueous plus 2 chlorines aqueous. And you can see how all the ions. I get 1 lead, also aqueous with a +2 charge. I get 2 nitrates, NO3 minus, with an aqueous charge. And so remember that nitrate, it doesn't really show up as NO3 minus as 2 of them connected, which is what you would be implying if you wrote it as NO3 2 minus, right? You're saying all of that is stuck together as 1 unit. It really shows up as 2 separate nitrate ions. And then from there, we can go ahead and turn that into the next one, which is our PbCl2 should stay together because it's a solid. And we should have our 2 sodium pluses as aqueous and 2 nitrates as aqueous. Sorry, running out a little bit of space there. We can take out our net or our spectator ions in order to do our net. So our sodiums are going to go, our nitrates are going to go. And so we get Pb2 plus aqueous plus 2Cl minus aqueous going to PbCl2 as a solid. And that's how you do your equations. And so you want to make sure that you have them balanced and you're going all the way through with them. Okay. Now there's a lot of ones for you to practice. So you can go ahead and do that. You can practice them as you go down. Yeah. And so I would really strongly encourage you to do all of these as you keep going through. It takes a lot of work, but this is also great practice for your first exam because it has you guys using your different naming, your nomenclature in order to practice moving from one thing to the other as you kind of go through. And then at the very, and then online, I'm also going to link the answer key on the next page so that way you can look at that as well. All right, good luck.